We learned yesterday, we learned what a relation was. Okay? And we learned different ways that we can represent relations. Okay? The day before that, we learned about the coordinate system and how that coordinate system relates to relations, because we can graph things on that. And the graph is a representation of a relation. Right, today we're going to learn about a special type of relation called a function. Okay? It's a specific style and scenario of what a relation is. It has specific characteristics about it. Okay? And we're going to use, I'm going to give you guys a true story, okay, about that. Okay? We'll have true story time today. It'll be epic. And then tomorrow, what we're going to do tomorrow with this stuff is we're going to practice it tomorrow, actually, more function stuff, okay, and what it means to be a function, different ways we can represent functions. And then on Monday, we're going to have a review day, and then on Tuesday, so part of tomorrow is our quiz, okay, and that quiz is going to be on the coordinate system, relations, and functions. Okay, so what we've been doing. Included in that is independent, dependent variable stuff, okay, which is why we did that. So I think I know what we need to do today.
No. If you said
Cozy on up.
I have to see the chubby baby.
Go. Okay. A relation. What did we talk about? What was a relation? What was a relation? Yeah.
It's like group of numbers or two numbers that relate.
To a comparison of two quantities, we can say, two numbers or two sets of numbers, okay, two sets of quantities, okay. One way we can represent relations by what ways? By a mapping, by a graph, typically by ordered pairs, and by tables, all sorts of different things. Okay, there's different ways to represent different relationships. Okay, a function, it's a special relation, a special kind of relation, very special. It's so we're going to say a function is a relation whose inputs only map to one output. Okay? Each input goes, each input gives only one output. What's almost a synonym for inputs? What's almost a synonym for an input? Starts with a D. Almost a synonym is a domain, the domain for inputs. For outputs, an almost synonym for it is the range values. Set of all inputs is called the domain. Set of all outputs is called the range. Okay, true story time. You ready? This is going to be epic. So I have this good buddy of mine. Okay, his name is Paul. Okay, Paul, who actually happens to be. Does anybody know John Herrera?
Yes.
Okay, it's his oldest brother. Okay, he's 31, by the way. Paul. Okay, used to have this house, and it had a detached garage, and we used to go and watch football games there all the time. Inside of said garage was a soda machine, an old soda machine, an RC soda machine. And so what Paul did in his garage was, when we were all over at his house, he just kind of got like annoyed that we would drink all of his soda, okay, and we wouldn't pay for it or anything. So what he did, yeah. So what he did is he said, okay, you can just pay for your own sodas, but I'll still bring you soda. Like you don't have to bring your own. Like I'll still go to the store and get it, because he had his soda machine. Why not? So what he did was he put the sodas in the machine, and then he charged us like 50 cents a soda, or like 25 cents. I can't remember what it was, but like super cheap, right? Just like essentially his cost. Okay, and so when we would get there, we would just buy the sodas ourselves instead of just taking his drinks. Okay, so we would bring like, and he would have change there, because the soda machine would be full of change. So if we didn't have change with us, we would give him $1, and he would just pull $1 out of the inside of the machine, stuff like that. Anyway, so on a soda machine, right? Soda machines work where there's buttons, right? You put the money in and you press a button. You with me? So hypothetically, say it's like a Pepsi machine, because that's way better than Coke. So button 1, say, is Pepsi, right? Blue, Pepsi. Okay. Button 2, Pepsi again. Button 3, Mountain Dew. And then button 4, let's just say lemonade. Okay. So say these are the different things inside the soda machine. Most soda machines work like a function. Okay? Most soda machines represent what we call a function. Okay? Whereas the input on a soda machine is the button you press. You with me? When you press a button on a soda machine, you get one specific beverage out, right? On Paul's, hypothetically say this was Paul's, when you press the blue button, you get Pepsi. You don't get Mountain Dew. Right? When you press the Pepsi button, that's exactly what you get. You only get Pepsi, right? When you press the green button, you get Mountain Dew. When you press the yellow button, you get lemonade. Okay? You press the button, you get a specific thing, one specific thing out. Okay? It's still a function. Even though on this particular one I've drawn, there are 2 buttons that are Pepsi, right? There are 2 buttons that are Pepsi. So you could press either button 1 or button 2 and still get a Pepsi. You with me? Okay? Still a function. You're still getting just one thing out, and you know what that thing is that's going to come out. You with me? Okay. That is a function, a soda machine that represents a function. Okay? Paul's machine was a little bit different, though. Okay? This is totally a true story. Okay? Paul's machine had a mystery button. And the reason why it had a mystery button was he would take all the sodas and he would fill up the different racks in it, and then what's left, in the cases, he would just throw inside the mystery button aisle. So when you press the mystery button, you didn't know what you were getting. Okay, Paul's soda machine was not a function, because you did not know when you pressed the mystery button, you did not know which one of the 4 or 5 different sodas was going to come out. You with me? Okay. Functions, you do a specific thing, you put a specific thing in, and you get a specific thing out. Non-functions, things that are not functions, you put a thing in, and you get 1 of 2, 1 of 3, 1 of 5. You're not exactly sure what's going to spit out. Okay? But you do know that there's something that spits out, right? But you're not exactly sure what's going to come out. That is not a function. Okay? With me on that? Okay. In terms of math, okay, there's ways that we can, let's backtrack. Hold on to the thought about the soda machine. Okay, we'll come back to that in a second. Okay, there's different ways. There's actually 5 ways, so scribble that out and write 5. There's actually 5 ways that we typically represent a function. We do it by a mapping. We've done that already. We do it by a graph. We've done that already. We've done an input-output table. That's a table. An XY value table. We've done that already. We've done we've done equations, but we haven't talked about them in terms of functions. We're going to do that today. Okay. The fifth one, what are we missing up there? We're missing ordered pairs. We can represent them by ordered pairs. Okay? All right, so let's look down below. We're going to talk about what it means to be a function based on the different examples. Okay? And I'm going to tell you why each one of these things represent a function. And then we're going to figure out which ones, like after that, we're going to figure out what does and what does not represent a function. Okay, so the first way we can represent a function is by mapping. Okay, whereas you got the domain, you got the range. Okay, this is a function because the number, -2, button -2, maps only to -3. Okay, button -2 gives us -3 out of the Coke machine, or the soda machine. Okay, on the soda machine, -2 is the button, -3 is what comes out. It's clear. There's only one thing that comes out for -2. You with me? On 0, only one thing comes out, 6. With me? On the input of 3, only one thing comes out, 6. It's okay that 6 comes out of 2 different buttons or from 2 different things. That's okay. What's important is that only one thing comes out for either of those things. Yes, the 0 and 3 would be like the Pepsi button on the soda machine up above. Okay? 2 buttons for Pepsi. It's still a function. Okay? There is no mystery button on this machine. Right? There's no mystery button. There's no input that you don't know exactly what's going to come out. Right? There's no question about what's coming out for each one of those inputs. The same thing is true with the second one on the graph. Okay? It's pretty clear on what comes out if you have a input value. If you remember, we talked about our inputs are typically our x's. So our inputs are everything that goes left and right in here. That's all the x values forever. Okay? Like 2.5 is an x value that's represented in this graph right there. Okay? 2.5 is an x value that's represented in this graph. Okay? On the function itself, which is the curve represents the function. It's a visual representation of the function. There is only one spot on that curve where the x value is 2.5. You guys with me on that? There's only one spot on that curve where the x value is 2.5. Just one spot. That's it. Okay. The same thing is true if we say like -6.9 repeating. So -6.9 repeating would be like there on the x's. In terms of y, we have to look at the curve to find out where on y it's actually the case, which would be right there. In terms of y, there's only one y that comes out for the input value or the x of -6.9 repeating. You with me? It's specifically on that spot on the curve, which is about like -9 point something or other would be our output or our y. Okay? There's only one thing that comes out with each y. If it was not a function, it would look like this. They would like overlap. You with me? Like if that was the curve and we were talking about 2 on the graph, 2 could be that spot right there, 2 could be this spot right there, or that spot. That means it is not a function because there's 3 different options for it to come out. Input-output table. For the input of 1, it only goes to one number 4. Okay? For the input of 3, it only goes to one number 2. Input of 5, it only goes to 4. Input of 7, it only goes to 5. This is a function. What would make it not a function is if I added another spot for 7 and I said it went to 2. If I said 7 goes to 2, that would make it not a function. Because the button that would represent 7, the number 7 button would either go to 5 or 2, we're not sure. That's like the mystery button. You with me? Okay, so when we're this would not represent a function if it was 7, 2. But what is okay is if there's 2 of the same, if 2 inputs go to the same output, it's okay. If 2 inputs give you the same output, it's okay. Okay, let's go on to what is and what isn't a function. Okay, on A, okay, we ask ourselves the question, does the value 2 go to two different things in these ordered pairs? Does the input value 2 go to two different things? That's a problem, isn't it? 2 is like our mystery button, though. We could either get a 1 to come out, or we could get a -2 to come out. That makes it not a function. With me on that? Makes it not a function. How about on B? Does the number 1 go to two different things? Do we know what comes out with number 1? How about with number 2? Do we know what's going to come out with number 2? Just the 5, right? Do we know what's going to come out with 3? Do we know what's going to come out with 4? Yes. There's only one thing. This is, yes, a function. On a mapping, in this, for input value -1, do we know what's going to come out for -1? We're not exactly sure, though. Two different things. We don't know specifically. If we press the button number 1, we're not sure what comes out. Number 1's like a mystery button right now. We don't know what's going to come out. Okay? We could have a 3 or a 9. Okay. So this one's not a function. And then on the last one, the smiley face. If you are, say, at x is 2, are there two spots on the graph, on the curve, that show up with 2? X being 2 is there, X being 2 is here. There's two different spots, at least. That means it's not a function because we don't know exactly what the value of y should be for the x value of 2. So it's not. Okay, let's go on to the next page. We're going to skip this. Okay. A function is a rule. I've been talking about how things are rules, okay, specifically on how things are rules. Functions are definitely rules, okay, in terms of equations. This is a function that's represented as an equation right here, okay, as 3 different equations, and there's actually 3 different functions there. There's a function machine f, right? That's the first one. There's a function machine g, that's the second one, and then there's a function machine h, okay? The way that they're written says function machine f takes x and does things to it. In particular, function machine f takes x, whatever x happens to be, multiplies it by 2, then subtracts 3. With me on that? That's what function machine does, okay? X in this case is like a generic button on the soda machine, okay? What 2 times -3 is like is what happens inside the machine. You with me? The result of using that function machine is the result of doing all this multiplying and this subtracting. With me on that? Okay. On the first one, f of 2, we say it f of 2. 2 is like the button on the machine. We're putting 2 in. Okay, we're pressing 2. Okay? When we press 2, we've got to stick it inside the machine. We have to multiply it by 2, then subtract 3, because that's what the rule says. Okay? And we get our result. We calculate whatever that result is, and that tells us what spits out for 2. Okay? Let's pause for a second and backtrack. What changes between this and this? Describe the change. Just say it. What happens? What changes? The x turns into 2. Yes. Say that again. X turns into 2 between those. So when I go ahead and use this rule, guess what we should do to the x? We should turn it into 2. But from here to here, the x turned into 2. So from here to here, guess what the x should turn into? 2. With me on that? We just put 2 inside the function machine. Now it's going to say multiply by 2, subtract 3. Do that math. 4 minus 3, 1. So what we're going to say as our final statement, we're going to say function machine f, when we put 2 inside of it, it turns out 1. Okay? That's what this statement says. It says f of 2 equals 1. Literally it means function machine f takes the number 2 and turns it into 1. That's the rule. Function machine f can do the same thing to -1. Notice how we can, it's just x gets replaced by a -1. With me in that? So we're just going to replace the x in here with a -1. So instead of writing x, we're going to replace it with a -1. So the function machine f takes -1, it's going to multiply it by 2 and subtract 3. And we're going to determine what comes out after we do that. Okay? 2 times -1 is -2 minus 3, right? -2 minus 3 is -5. So as our final statement, we're going to say function machine f takes the number -1 and turns out, no pun intended, turns out -5. Okay, you with me on that? Let's do the third one. Function machine f takes 0, multiplies it by 2, and then subtracts 3. So 2 times 0 is 0, minus 3 is -3. So function machine f takes 0 and turns it into -3. Okay? We say that f of 0 equals -3. We're not going to divide by 0, because that's not what that says. That's not f times 0. That's just f of 0. That's function machine f takes 0 and turns it into -3. Okay, let's skip all the way down to the bottom here. That was our function f. Somebody describe to me what happens here. What happens here? Function f takes -5, right? Turns it into something, some other number, and then afterwards we have to add 7 to it. With me on that? So we're going to use function machine f on -5, and then afterwards we're going to add 7. Okay? So we're going to say function machine f takes -5, multiplies it by 2, and minuses 3, right? But to show our appropriate work, just so we don't get lost, we're going to drop that plus 7, so we say this is what happens afterwards. Okay? We calculate that. -2 times, or 5 times -2 is -10, minus 3 is -13. So then we do -13 plus 7, which is going to be -6. So what we're saying is function f of -5 plus 7 is going to equal -6. Or we can just leave -6 as our answer, because writing it all together is really confusing looking. So our answer is -6. Okay, we're going to do it again. I'm in trouble. We're going to do it again. But the next one is a different machine, right? The next one is machine G. What up, G? Machine G. Machine G says square the number and then add 3. Okay, that's the rule. That's the machine G. But in this one in particular, we're going to first figure out what machine G does to 8, the value 8, and then at the end we're going to multiply it by 2. Okay, so what we're going to do is at the end, we're going to end up multiplying it by 2, but function machine G is going to take 8, so we're going to replace x with 8. Okay, with me on that? We're going to change x to 8. Okay, we're going to figure out what function machine G does to 8. 8 squared is 64. 64 plus 3 is 67. And then we're going to multiply it by 2, which is going to be 134. That's right? Okay, on the last one, we're talking about function machine H is going to be -x plus 7. Function machine H of x is going to be -6 plus, or -x plus 7. On the first step, we're saying use function machine on 5, figure out what that is, then subtract it from the function, what the function does to -7. So for this guy, we're going to do -5 plus 7 for the first set, Then for the second set, we're going to do -7 plus 7. Notice we replaced x with 5 in the first set, and then we replaced x with -7 in the second set. Okay, and we're going to figure out what that winds up becoming. So this is -5 plus 7 minus negative is going to be positive plus 7. -5 plus 7 is 2. 2 minus 7 is -5. Answer is 2. Okay. That's all we have today. We do have a worksheet. It's going to be on the table. I will also post it online. If you do it online, if you're doing it online and you don't have the printout at home, you can just do it on a separate sheet of paper. Okay?